Look around you. The universe is just full of rhythm, isn't it?
Absolutely.
Your heartbeat, the swing of a pendulum, the moon going around the earth, steady, reliable.
Mm.
And numbers, well, they seem to have their own music too, right? Like 2, 4, 6, 8.
It's very predictable.
Yeah, or multiples of 10. They feel like these dependable drum machines on the number line. They set down a beat, a cadence you can count on.
And you know, that feeling about mathematical rhythm, it's ancient. Think
Yeah.
about the Pythagoreans.
Yeah, the music of the spheres.
Exactly. They believed the whole cosmos was built on these, like, musical ratios.
Mm-hmm.
Now, we don't think of it quite so literally anymore, but that search for elegant order in numbers, still fundamental.
Right.
And the study of these patterns, these arithmetic sequences, it actually started from really practical things, trade calculations, building design, stuff like that.
But then you have the rebels, the numbers that, well, they seem to march to their own beat.
The primes.
The primes, only divisible by 1 in themselves. 7, 13, 179. They're like the essential atoms of arithmetic, the indivisible building blocks.
That's the fundamental theorem of arithmetic, basically.
Yeah.
Every whole number bigger than 1, it's made from a unique set of primes multiplied together. It's absolutely foundational.
But how they appear? For centuries, it just looked completely random.
2, 3, 5, 7, 11, 13.
Yeah, there's no simple tune there. It's like cosmic static, just noise spread out across this infinite number line.
Right.
And mathematicians looked at this chaos, and they wondered, is this just beyond us? The great Carl Friedrich Gauss, a guy who saw patterns everywhere.
A legend.
He famously suggested that finding order in the primes was one of those problems which the human mind will never solve. The feeling was, yeah, we can find them one by one maybe, but predict them. Find some deep structure, probably not.
And you can see why they thought that,
Yeah.
given the math they had back then. That apparent randomness, it felt like a brick wall. The big shift came later, trying to understand not just individual primes, but their overall distribution, how they're spread out.
But what if that's not the whole story? What if deep inside that static, buried under all that noise of infinity, there are these secret drum beats, rhythms we just haven't learned to hear yet? What if some of these rebels, these cosmic hermits, are actually marching in formation secretly? That's really the question for this deep dive. Can we find rhythm in the prime number static? And spoiler alert, the search for an answer led to something totally revolutionary, a new kind of mathematical tool.
A paradigm shift, really.
Okay, so to even start thinking about this infinite ocean of numbers, you need some solid ground, a starting point. And the first really crucial foothold, that came from Euclid of Alexandria, way back, like 300 BC.
Yeah, in Alexandria, that incredible hub of ancient knowledge.
He gave us this proof. It's just a masterpiece of logic. He proved that the primes are infinite. There's no end to them.
It's in his famous work, The Elements, which was just foundational for centuries. And his proof about primes. It's one of those elegant arguments in math, a classic proof by contradiction.
And the idea is so simple. It's beautiful. Just imagine you could actually list all the prime numbers.
A finite list.
Right. Call them P1, P2, all the way up to the very last one, Pn. Euclid says, all right, let's multiply all those primes together. You get some enormous number. Let's call it n.
N equals P1 times P2 times, all the way to Pn.
Okay. Now, just add 1 to that giant number. Consider n plus 1. This new number, n plus 1, it has to be one of two things. Either it's prime itself,
A new prime.
or it can be divided by a smaller prime number. It's composite.
Right.
Okay, so case 1, if n plus 1 is prime, well, boom, you just found a prime number that wasn't on your list, which you said was complete. So your starting idea that you could list them all must be wrong.
The assumption fails.
But what if n plus 1 isn't prime? What if it's composite?
Right.
Well, that means it must be divisible by some prime number. But which one? Ah, here's the clever bit.
Can it be P1, the first prime on your list? No, because if you divide n plus 1, which is P1, AP2, APN, plus 1 by P1, you get a whole number part, P2 by APN. But then you have that leftover 1, a remainder of 1.
Exactly. Dividing n plus 1 by any prime on that initial list, P1, P2, any of them, always leaves a remainder of 1.
So none of the primes on your original list can divide n plus 1 evenly.
Meaning, if n plus 1 is composite, its prime factors cannot be any of the primes you started with. They must be new primes.
Exactly. So whether n plus 1 is prime itself or it's composite and needs new prime factors.
Yeah.
Either way, you're forced to admit there has to be a prime number that wasn't on your original list.
The list can never be complete.
Therefore, the primes go on forever. Infinitely many.
It's just such a powerful piece of reasoning. Stood the test of time for over 2 millennia. It guarantees this endless supply of prime building blocks.
It's stunning. It
Yeah.
sort of tames infinity just enough to show us it's limitless, but, and this is the really important part.
Knowing the ocean is infinite doesn't actually help you navigate it, does it? It doesn't tell you about currents or specific paths or hidden structures within it, just that it's big.
Precisely. It proves existence, not distribution or pattern.
So, okay, we zoom in. We move from this vast infinite ocean to a more specific question, a more maybe human question. Can we find a single steady rhythm pulsing inside all that static?
Right.
Will primes keep showing up if we just follow a particular beat on the number line?
This is the shift from are there infinitely many to how are they arranged? And an arithmetic rhythm or sequence is just where you start somewhere and keep adding the same amount, like 3, 6, 9, 12, adding 3 each time.
Or 5, 10, 15, 20, adding 5.
Yeah, and the specific question here is about a sequence like, say, start at 3 and keep adding 10.
Let's use that example to add 10 rhythms starting at 3. The sequence goes 3, 13, 23, 33, 43, 53, 63, 73, 73, 83, 93, and so on. You notice they all end in the digit 3.
Mm-hmm.
Now let's check which of these are prime. Okay, 3 is prime, 13 is prime,
Yeah.
23 is prime.
Still good.
33, nope, that's 3 times 11.
Composite.
43 is prime, 53 is prime, 63, nope, 3 times 21, or 7 times 9.
Right.
73 is prime, 83 is prime, 93, nope, 3 times 31.
Okay, so quite a few primes showing up there.
Yeah, it definitely looks like they keep appearing in this ends in 3 pattern.
And notice something important. The starting number, 3, and the step size, 10, they don't share any common factors other than 1. We say they're coprime.
Ah, is that important?
It's critical. If they did share a common factor bigger than 1, like imagine starting at 6 and adding 10, you'd get 6, 16, 26, 36.
They're all even, except the first one maybe. Wait, no, they're all even.
Exactly. They all share the factor 2, which 6 and 10 have in common. So beyond the first term possibly, none of them could be prime. For infinite primes to even be possible in a sequence like this, the start and the step size must be coprime.
Okay, that makes sense. So 3 and 10 are coprime, and it looks like primes keep popping up. But how can we be sure? How do we prove this isn't just some weird coincidence that stops after, I don't know, a trillion steps? When the numbers get astronomically big.
That's the much harder question.
Yeah. How do you find that single repeating signal, that one specific drumbeat inside an infinity of what looks like cosmic static?
For a long time, mathematicians looked at prime tables, saw these patterns empirically, like Legendre and Gauss did. They noticed primes seemed to fall roughly equally into the valid sequences, like ending in 1, 3, 7, or 9 for the add 10 case. But observation isn't proof. They needed a tool, a rigorous way to analyze it.
You need like a special kind of telescope for numbers.
Something like that.
And for the last century and a half, the closest thing math has had to that kind of prime number telescope, the tool to study their grand architecture, has been the Riemann Zeta function.
Introduced by Bernhard Riemann, 1859. Building on Euler's work, actually, it's a function from complex analysis. But the concept, you can think of it as a bridge.
A bridge?
Yeah, connecting the discrete world of numbers, like the primes, to the smooth, continuous world of mathematical waves and surfaces. Analysis.
Okay, don't need the nitty-gritty formula maybe, but what does it do?
By studying the shape, the sort of topography of this function, mathematicians can uncover deep truths about how primes are distributed.
Like what?
Well, it's the key behind the prime number theorem that gives you an estimate for how many primes there are up to a certain large number. Its structure is also tied to the most famous unsolved problem in math, the Riemann hypothesis.
$1 million question.
That's the one. The hypothesis suggests a hidden regularity in the primes, linked to where the zeta function equals 0. It's incredibly powerful for understanding primes as a whole, their overall density and behavior.
So this sounds like the tool, a mathematical marvel. It feels like it should crack everything about primes, right? Our biggest, most powerful weapon.
You'd think so.
But here's the twist. Here's where it gets interesting. For our question, for our specific, simple-sounding quest, do primes keep showing up in the sequence 3, 13, 23, and so on? The Riemann zeta function. It's almost completely useless.
Yeah. Despite all its power for the big picture, the standard zeta function just can't isolate primes within one specific arithmetic progression like that. It can't tell the patterns apart.
The greatest tool in number theory, blind to our specific rhythm. Why? Why does it fail here?
Well, think about that orchestra of primes again.
Okay.
The Riemann zeta function is like one giant microphone hanging over the whole concert hall.
Right.
It hears everything. All the notes from all the primes mashed together, gets the total sound, the overall volume, the combined harmony, maybe the average tempo.
I see where we're going.
But you can't use that one microphone to listen only to the second violin. Or in our case, only to the primes ending in 3.
It hears the ends in 1 player, the ends in 7 player, the ends in 9 player, all mixed up with our ends in 3 player.
Exactly. The way the zeta function is built, using its Euler product form, it inherently combines contributions from all primes. It gives you the aggregate picture, the total sum. You can't easily pick it apart to hear just one instrument, just one sequence.
So our question isn't about the whole symphony. It's about that one player, the one hitting the notes ending in 3. Do they keep playing forever? Does that sequence contain infinite primes? And the zeta function, our best tool, it's like a net for the whole ocean, not a fishing rod for one specific type of fish in one specific current.
A good analogy. It averages things out too much for this particular question.
So here's the impasse. A simple, elegant question, a hidden rhythm, maybe, and the most powerful tool we have for primes, deaf to it. The problem just looks intractable again. The static seems destined to just stay static. Feels like a dead end.
It was a genuine barrier. It showed that while analysis was promising, the existing tools weren't fine-grained enough.
Most people might have just given up there. But this is where genius steps in, right?
Precisely.
In the 1830s, actually, before Riemann's big paper, there was this brilliant German mathematician, Peter Gustav Lejeune Dirichlet.
Dirichlet.
He looked at this exact problem. He understood the potential of using analysis, continuous functions, curves, to study discrete things like primes. He saw the power, but he also saw this very specific limitation.
And Dirichlet was perfectly positioned. He had this rigorous German training from Gauss's school, but he'd also studied in Paris.
Ah, Paris. The hub of new analysis back then. Fourier, Cauchy.
Exactly. So he could bridge these two mathematical worlds.
Yeah.
The algebraic number theory side and the cutting-edge analytic method side.
And he realized you don't need a better microphone to hear more total sound. That's kind of what the zeta function does. You need a filter. Like how your brain in a noisy room can somehow filter out all the chatter and let you focus on just one voice. Dirichlet thought, what if we could build a mathematical function that does that? A function that filters out the noise from other prime patterns and listens only to the rhythm we care about, like the ends in 3 sequence.
This was revolutionary. Utterly.
Right.
Functions were usually seen as these objective formulas, apply the rule, get the output. Same rule for everything.
Right.
Dirichlet imagined functions with character. Functions that could be selective. Picky, almost.
Exactly. A function with preference, with personality. A mathematical tool that could look at the number 13 and say, yep, you match my pattern, you're in. But look at 15 and say, nope, ignore you. How on earth do you bake that kind of selectivity, that character, that preference, into cold, hard math?
It wasn't just applying known math cleverly.
No, it meant inventing a whole new kind of mathematical object, a totally new way of thinking about what a function could even be.
He invented what we now call Dirichlet characters. And conceptually, they're exactly those filters he imagined. They're functions designed to pick out numbers based on their remainder, their pattern, when divided by the step size.
So one character could listen for ends in 3 when adding 10, another could listen for ends in 1, and so on.
Precisely. They essentially use roots of unity, complex numbers, to tag numbers according to their congruence class, their pattern.
Yeah.
And crucially, he figured out how to combine these character functions using their orthogonality properties, essentially using them to cancel out the noise and isolate the signal from just one sequence.
Wow, okay. And this invention, this incredible idea of mathematical filters, did it work? Did it solve the problem?
It did. Completely. Dirichlet used these character functions to prove, back in 1837, that for any arithmetic sequence where the start and the step are coprime, like our 3 and 10 primes, do appear infinitely often in that sequence.
He proved it. The static could be filtered, that specific drum beat, it exists, and it goes on forever.
Yes. And this work, it was so much more than just solving one problem, important as it was. By creating these characters and showing how to use them with analysis, Dirichlet basically founded the entire field of analytic number theory.
Analytic number theory. Oh, okay.
He showed how to fuse abstract number questions with the power tools of calculus and analysis. He created things called L functions, which are like generalized zeta functions using these characters. Proving a key property about them, that L1 is non-zero, was the linchpin of his proof. This whole framework opened the door for so much that came later in understanding primes. The single drumbeat became potentially a whole symphony of patterns.
So why does this whole story matter? Why should you care about primes ending in 3 or these
Where
character things?
Wow.
Because it shows something profound, I think. Even in something that looks like pure, absolute randomness, like the primes seem to be, there can be deep structure, hidden patterns. But sometimes the tools you have just aren't right for seeing it.
Yeah.
You have to step back. You have to think differently. You might need to invent a completely new tool, like Dirichlet did, a tool designed specifically to filter out the noise and zero in on the signal you're hunting for.
It's a huge lesson in innovation, not just in math. Sometimes the breakthrough isn't more data or more power. It's a fundamentally new perspective and a new kind of lens.
We invented a mathematical filter, a function with character, to finally hear those hidden drum beats in the static of the primes. And it makes you wonder, doesn't it?
What else is out there?
Yeah. What other complex systems? In the universe, maybe? Or even just in our own lives? Biology, society, economics. What hidden patterns, what signals buried deep in the noise are we completely missing right now? Simply because we haven't invented the right kind of filter yet. Because we haven't developed the right character, the right specific tool or viewpoint to even perceive them. What can we really learn from Dirichlet about tackling problems that seem impossible just by thinking differently about the tools we use to look at them?